Hello, everyone. Come on in. Come on in, everybody. Anybody have any questions before we get started? You're welcome to go ahead and ask them now as well.
I've got a question.
Yes.
I was just wondering, I was just following back up on the email I sent you a couple weeks ago. I was wondering.
Yes. Who's this speaking anyways? Let me double check.
This is Sarah.
Yeah. Didn't I send you an email about that?
I didn't get an email back.
Okay. I did send an email. Where that went then? That's weird. Let me check and see if it's in my folder. That's weird. Maybe I sent it on my phone. That might be it. Actually, I had a couple weird things occur the other day. It turned out I had filled out a proctoring form for the testing center and it never went through either. So I'm wondering if you might have had the same thing happen to you. Let's see my sent mailbox.
Professor?
Yes.
I have a quick question about the test. I wasn't here if you had answered this question already, but I was wondering what test are we taking Wednesday?
Okay, so so this is chapter 8 and 9 that you'll be taking Wednesday. I discovered a problem with what I'd set up the other day. I forgot that our midterm was on chapters 1 through 6. So I reopened practice test 3, I think it was, with chapters 5 and 6 on it. But I also opened chapters, I think 8 and 9. So the 8 and 9 is what the test is going to be on Wednesday.
Okay.
And I went ahead and opened. Yeah, sorry about that. That was a screw up. But I've noticed most people have already taken it a couple of times, so that's good. By the way, since I opened practice test 3 up on chapters 5 and 6, some of you had not taken it. Remember when I go through and at the end of the semester, I take the average highest score from each of the practice tests I made. That happens to be one of them, and I divide that grade by 20. The average of the highest grades by 20. If you got a 0 in there, you're getting no better than 4 points. So y'all might want to take the little bit of time you got left to take that a couple of times. But the test on Wednesday will be on Wednesday will be on chapters 8 and 9.
Gotcha. Thank you.
You're welcome. And I opened up practice test. You'll see the practice tests that I was just talking about, 3 and 4. You'll see them in week 7 module. I just opened up week 8 module, and in there you'll see chapter 11 and chapter 36 homework, as well as practice test 5, which covers 10, 11, and 36. And you'll actually see test 5, which is going to be an online test taking place of the other one that I missed. But instead of it being due on Monday, on Sunday, it'd be due on Wednesday, July 20th at 11:59 p.m. So if you look in module for week 7, you'll see those two, that practice test and the actual test is already available. So you can take it as early as you want to, but you need to take it by July 20th. That's the main thing. And I do not see the email that I sent you, Sarah. So can we talk at the end of class? That was Sarah that I had spoken with earlier, right? I did see the one where I responded to Nora.
Yeah, that's fine.
Okay. I'm sorry. I'm sure I dropped the ball on something, and I apologize, Sarah. I don't know what I did, but I'm sure I did something stupid. So anyways, I will make it up to you. I will fix something or do something to make it up for you. We got another person coming into the classroom. So if also you might not notice, I've sort of already covered chapter 11 in the previous topic when we were talking about chapter 10. When I went into angular momentum, that was a quick cursory coverage of chapter 11. Very, very quick, very, very cursory. But you'll see the types of questions that I'm asking you on that will be in tests as well as in the final exam, as well as in the homework. So pretty straightforward. So I don't think you'll need more than that, but you certainly can have more than that. All you have to do is ask me if you have any problems. I've posted numerous videos already on chapter 36 in this week's module, and last week's module I had a bunch of chapter 10 videos. I'm going to link some more for chapter 11 in this week's module. I haven't done that yet. So you'll just have a little bit more experience. The main type of topics I want you to be prepared to do is, one, understand under what conditions is linear momentum conserved, because that was what came from rotational motion and Newton's second law. Linear momentum came from when we covered the chapter on momentum, which I think was chapter 9. So there was a very specific case that had to be, our thing that had to be true for momentum to be conserved. Then under what conditions is angular momentum conserved? And it's a very analogous case to that. Under what conditions is kinetic energy conserved? And under what conditions is energy conserved? Those are all topics that you should know now and be able to answer immediately right now without looking it up. If you don't, that's okay. I'm giving you, that's a warning. Make sure you can have that, because sometimes I might get a wild hair and just decide to ask you a simple question like that on an online or a face-to-face test, and it's me trying to throw free points at you. So if you don't know those basic things, what is Newton's first law? What is Newton's second law? What is Newton's third law? And which one's which? In other words, what are Kepler's first law, second law, and third law? Under what conditions is momentum conserved? Under what conditions is angular momentum conserved? Under what conditions is energy conserved? And what conditions is kinetic energy conserved? Those are just fundamental questions you should know the answer to. So just keep that in mind. That's me giving you a little hint that sometimes questions like that pop up and they're supposed to be really easy free points. But if you didn't think that was that relevant, then you might not have memorized it. Anybody else have a question? Okay, so I have posted this week 8, which is July 11th through July 17th. Right now, all I have up there is some special relativity stuff, which is what we're covering tonight. I'm available next time, of course, if you have any more lingering questions on chapter 11. Again, because like I said, it is a short coverage that I did. And if you had any questions on any of the videos that I post up there. And I have a practice test 3 that's up. That's because I forgot that we had already been tested on that. But it's another opportunity up until July 17th for you to get practice test 3 with a grade other than 0. So if y'all haven't taken that, make sure you take it before July 17th. Practice test 4 is up, and that's in preparation for your test on Wednesday. That will be, administered face-to-face in the lab with Mr. Mitchell. And then in week 8, you have practice test 5 and actual test 5. But you'll see that those due dates are July 20th. Okay, so hopefully that should keep you all straight. And I apologize for bungling that plan of those practice tests and stuff. So now, any questions?
Professor?
Yes.
I just saw your email. Thank you so much for responding. I really appreciate that.
You're welcome. Yeah, I know. That reminds me of something. I know you guys are probably a little stressed in the summer. A 10-week semester is a brutal thing, and a 10-week semester in calculus-based physics is super brutal. I actually had 3 students that had to miss over 2 weeks of semester just because of COVID, stuff like that, and various other political issues that have come up that's depressing people, and that's good. I mean, if they're happy or glad or sad or whatever, either one, I like the fact that people in their college years are paying attention to what's going on in government at all levels. So certainly I understand. We're just going to have to keep doing as good as we can for a given situation, and it'll all work out in the end. And probably the best thing I've heard is people say it has been a lot worse. So let's sort of keep our eye on that, maybe as a positive aspect. So tonight we're going to start chapter 30. Actually, we're going to finish and start chapter 36. Chapter 36 is on special relativity. And special relativity was something Einstein came up with and published in 1905. And in fact, in 1905, he published like 7 papers or something, and 5 of them could have won him the Nobel Prize. Roughly speaking, it's probably more like 3 or 4 could have won him the Nobel Prize, not really 5. But anyways, he wrote a paper on Brownian motion using statistical mechanics, which is like it's what we go to when we don't know anything about physics or a certain specific area, because we realize when we talk about atoms and molecules at such a small scale, they're going to act very predictably because of the large numbers. So we use that, and it's in fact, it's so powerful. Einstein said if we ever solve all the questions of physics, it would probably be by statistical mechanics. And that's what he did. He just used statistical mechanics to work out what would happen if atoms existed, and you assume, say, a glass of water is made out of atoms / molecules. What would happen to the little dust particles or pollen particles on top of it, given what we believed at that time atoms were like. And basically, he was able to predict exactly how atoms would cause those pollen particles to behave in such a situation. And then they verified that he was exactly right. So really, the person that concretely finally convinced the world that atoms existed was Einstein in 1905. He also wrote a paper on the photoelectric effect, which is basically that when you shine the light on a pure metal, it actually works with all metals, but a pure metal is a little easier. It can actually generate a current. And you can do that with light behaving as a wave, but it acts quite a bit different, as you'll learn when y'all get to quantum mechanics next semester. But there would be like a delay, because first the waves have to get the thing in a resonant motion until it gets up enough energy. Then the brighter the light, the more current you would get. And those two things do not behave that way when you shine light on a metal. So Einstein used Planck's hypothesis that there exists little quantums, particles of light, which we now call photons, and that their energy is given by h Planck's constant times f, the frequency of the wave, if you're pretending it's a wave again, right? Or it can be h times c over wavelength, which is lambda. Both of those work fine. And what he realized is that when you imagine that light is made up of these particles, they either have enough energy, which is given by h times frequency. They either have enough energy to dislodge an electron from an atom so that electron can be used as a current, or they don't. So he figured there should be some turn on frequency, some lowest frequency at which you'd get a photoelectric current. And then the amount of current would just then be proportional basically to the number of those electrons that could be set free. So he predicted a very specific result. In fact, it was a graph, a linear graph that he predicted, and that's what won him the Nobel Prize. He then also predicted, or basically wrote a paper, I think the name of it was On the Electrodynamics of Moving Bodies, which is kind of weird in retrospect, because we're not going to mention electromagnetics very much at all in this course, much less in this chapter. So it's kind of weird. But what he's saying there is, by the time Einstein comes along, Maxwell is dead for 40 some years. I think Maxwell died in like 58 or 65 or somewhere around there. Horrible death of stomach cancer at a really young age, like 44. But he had written out Maxwell's equations. A lot of people just didn't really pay him attention because they were very complicated. But there was more or less 3 guys that really knew Maxwell was onto something, even though Maxwell pretty much just used Michael Faraday's notes and just turned them into mathematics. But he turned them into a branch of mathematics that was quite complicated. So Oliver Heaviside actually created vector calculus along with Gibbs over here in the United States, of Gibbs free energy fame. I think it was Gibbs. Those 2 guys both independently invented vector calculus and wrote his equations in vector calculus form. Again, a lot of people didn't know that branch of mathematics either, so they pretty much just didn't pay him much attention. In the intervening period, it was shown definitively that Maxwell's equations were on the money, and by the time Einstein comes on the scene, he knows Maxwell's equations are awesome. Well, the cool thing about Maxwell's equation, or the weird thing that Einstein noticed, is that when you put the equations together, and Maxwell knew this too, he predicted, and in fact was the first one to tell us that light was a wave based on actual equations, not just based on experiments, but based on equations that he derived from experiments. You could make a wave equation with Maxwell's equations, and it didn't matter if you made it for a reference frame that's sitting perfectly still, or if you made it for a reference frame that's moving at, say, half the speed of light. In fact, the equation was exactly the same. That caused some paradoxes when Einstein was analyzing it with what he calls his Gedanken, his thought experiments. So he would think of this, scenario like I'm riding on a beam of light and I got my mirror in front of me. And normally what happens with you looking at the mirror is basically photons from your face are sort of reflected off of your face to the mirror, and then off the mirror and come back into your eyes, and that's how you see your image. But when he imagined doing that riding on a beam of light, there were little paradoxes like, you couldn't see your image, or you get a certain distance away and you'd never be able to see your image, little weird stuff. It was just really paradoxical, and paradoxical really means two equally valid interpretations of something that are contradictory of one another. That's what a paradox is. It's not just something that's weird. A paradox literally means two equally valid conclusions, but that are mutually contradicting. So if you can't have one and have the other, in other words. So he had found a bunch of those. So really what he was saying was, hey, Maxwell's equations are right. And the only way I can make sense of that is if the reason that we don't have a different version of Maxwell's wave equation for different moving reference frames is because the speed of light is a constant independent of the motion of the source or the motion of the observer. So that's really what motivated him. And in fact, the equations of Maxwell that we learn in electricity and magnetism are in fact already relativistically correct. They didn't know anything about special relativity in the 1800s, but Maxwell's equations were fully formed by 1865. And in 1865, they had already predicted special relativity, but it took Einstein to actually see it. So Einstein writes his paper on the electrodynamics of moving bodies. And it basically has two principles. The first principle is the principle of special relativity. And it says the laws of physics are the same for all inertial observers. Now, when we switch to general relativity, the only thing he's going to do is remove the word inertial. So the laws of physics are the same for all observers is what he's going to do. But right now, that seems very odd. I hope it seems odd to you for him to say that the laws of physics are the same for all inertial observers. Because what the crap's an inertial observer? Well, an inertial observer is an observer that does not see any sort of quote unquote magical forces happening. Okay. For instance, any frame where Galileo's law of inertia, which basically says that it's as if an object has a certain reluctance to change its motion and therefore does not change its motion unless some force acts on it. That's Galileo's version. Or in Newton's first law form, an object in motion will tend to stay in that state of motion unless acted upon by a net external force. So when he says an inertial frame, he means those laws are held. So for instance, let's take a video camera and I'm going to mount it to one of those merry-go-rounds that you see in parks. The one that you push by yourself, or if you watch Tosh.0, you've probably seen people connect a motorcycle to one, sling people out like Sim City or something like that in their various games. But and don't try that; it's super, super, super dangerous. But anyways, if you mounted a camera to such a merry-go-round, such that you could only see the flat plate of the merry-go-round, you couldn't see any of the land around it. Since it's fixed to that plate, you would have no idea whether the merry-go-round's rotating or not. But what you would see, if maybe you stuck a basketball, say, dead center, you would see the basketball sitting perfectly still, and then all of a sudden it would not only move, but it would accelerate out of the screen. What that means is something just accelerated with no force that you can see. Well, that's exactly what our solar system looks like if we flew up over our North Pole and then got high enough up where we could see the Earth, Mercury, Venus, and then Earth. we would see the planets with nothing acting on them, not only curving as they go around the Earth, but also speeding up and slowing down, like according to Newton or Kepler's second law. So that's really what he's doing, is he's trying to cut out gravity, because he says gravity violates the law of inertia. Unless there's some magical force called gravity that reaches out over space, which clearly we had done a lot with physics based on that. Newton didn't like it either. Newton was bothered by the fact that he had to imagine some force reaching across space. It's called action at a distance, without anything actually physically touching it. But he realized also, well, now I can explain the tides, and now I can explain why the moon orbits the Earth. I can explain why the Medicean moons, Galilean moons is what they'll ultimately be called. He could explain those, which actually he didn't know about them then, but still the point stands. He can explain all sorts of motion, asteroids, comets, all sorts of stuff like that. So it was better not to worry too much about the bigger question of how in the crap is that force acting, and use it as we had it, because we could do so much with it. So everybody since then as well was very much bothered by it, or at least somewhat bothered by it. And Einstein was bothered by it. And that's what Einstein ultimately sets out to correct. And he does correct it in 10 years later, 1950. So the special theory of relativity, the first principle is the laws of physics are the same for all inertial observers. So that's him really trying to take gravity out of it. Of course, he'd also take that rotating disk out of it, but you can actually attack that with special relativity. It's just a little bit more complicated. And then the second law, the second principle of the special relativity, is the constancy of the speed of light. And it's basically saying that light has a very distinct property that nothing else does. And that distinct property is that its velocity, it does not change. Its velocity is always going to be, and we've now defined time and distance units such that it's exactly this figure. The speed of light is 299,792,458 meters per second, to an infinite number of decimal places, no matter how fast it's coming towards you, and no matter how fast the source is moving away from you, no matter how fast you're running towards the source, and no matter how fast you're running away from the source. It's always going to be, if it's in a vacuum, 299,792,458 meters per second. Okay, that's the weird thing about special relativity. That's the weird thing about light itself. Now, light does slow down. For instance, when you run light instead of into a vacuum, when you run it through a glass, it basically slows down by a factor of 2/3. And that might be water. Water does, one of them does like 1.2 and the other one does like 1.5. I can't remember which, but basically the index of refraction that you learn about in optics is basically a ratio of the speed of light divided by the speed of light in that material. So when light goes through something other than a vacuum, it does slow down, but that's still the fastest speed there is. And it still goes only that speed, independent of the motion of the source or the motion of the observer. So, for instance, if you're on the back of a flatbed truck, and let's say you can pitch at 90 miles per hour, you're standing on the back of a flatbed Mack truck, say, and the flatbed Mack truck is headed due north at 60 miles per hour. If you take and throw in the same direction that truck does, and you can pretend this motion could be watched without changing for a whole hour, at the end of 1 hour, the truck will have moved 60 miles, because it's going 60 miles per hour, 60 miles to the north. And from that spot on the trailer where the ball left your hand, from that to the ball will now be an additional 90 miles away. So the total distance traveled by the ball would be 60 plus 90, or 150 miles. In other words, the ball would travel at 150 miles per hour. That's true, and that's what we learned in Galilean relativity. That's the way velocities add. But if it's the speed of light, it doesn't add like that at all. In fact, if you're standing in front of the Mack truck and the Mack truck is coming at 60 and turns on its headlights, let's say the Mack truck is traveling at 3/4 the speed of light, not 60 miles per hour, actually 3/4 the speed of light, say, and it turns on the lights, you will measure the lights as coming to you at the speed of light. Now, if that Mack truck is coming towards you and you are actually riding the front beam of light, the front of the beam of light from the headlights of the Mack truck, and I shine a light at you, you're still going to measure that light coming to you at C, even though you're, traveling on a beam of light that's moving at the speed of light away from a truck that's moving at 3/4 the speed of light. That's the weirdness of relativity. So you'd think that's interesting. Yay, Einstein giving us that. Ooh, we can actually take our wave equations and say they're not going to change because we moved to a different reference frame. Way, but that wouldn't be that big a deal, right? Well, it takes a little bit of ingenuity for you to start to make something make sense out of that. So let me start by showing you in my sharing screen mode. I'm going to show you one of the ramifications of that. Okay, so one of the ramifications of that, as I screw my pin top on, is let's imagine 2 train cars. Okay, and these train cars have this neat thing that basically there's a little antenna here and here, and when lightning strikes like that, it actually causes a beam of light in the center of the car to actually shoot out both towards the front and the back of the car. Okay, well, let's say that this car is moving at a velocity v, and you have one observer here, O1, and another observer here, O2. Okay, now O1 riding in the car would say, wow, that's really neat. A beam of light left the light in the middle of the car and in fact hit the back edge and the front edge simultaneously. So you would say the light hitting the back edge of the train car is simultaneous. I'm going to switch colors to make sure this makes sense. Okay, but now let's see what, that's according to O1. Now let's see what O2 saw. Well, what O2 saw was lightning strike, and then the train car moved ahead a little bit, and then moved ahead a little bit more, like this. And what it saw was that the back edge of the train car was headed towards the light. So in fact, the light hit the back, and I'll make this one green. Light hit back first. That's according to O2. Okay. And then sometimes later, it hits the front. Again, that's O2 that saw that. And the reason why you would say normally under Galilean relativity, well, since the light was emitted from a light bulb that was moving at V, then its velocity forward will be V plus C, and its velocity backward would be V minus C. And we'd agree, in both O1 and O2 would agree that the two events were simultaneous. But according to Einstein's theory of relativity, the second principle, the speed of light is not going to be increased by V, and it's not going to be decreased by V. It's just going to be C. So that's why in train car 2, observer 2 is going to say, no, the light actually hit the back first because the back was moving towards the light, and the light was moving at C in the backwards direction. And then it hit the front because the front was moving away from the light, and the light was moving at C, not C plus V, not C minus V. So that's the first thing we've already lost. And you can see how by employing light, we can make some sense of what the principles of relativity give us. Okay, the first one being the laws of physics are the same for all inertial observers. And in that case, what we mean is that neither O1 nor O2 are wrong about what they observed. They're both correct. Okay. The light hitting the front and back of that top train car was simultaneous in one frame, but in another frame, it was not simultaneous, and that's just fine. But that does bring into question or introduce us to the fact that light moving at a fixed speed alters stuff. And, you know, the speed of light, like any speed, is given by distance traveled divided by time taken. So you can see, since the distance traveled over time taken has to be a constant, if you mess with the time, you've got to mess with length as well. Or if you mess with length, you got to mess with time as well, because you've got to always fix the ratio such that it's 299,792,458 meters per second. So C, as I said, was 299,792,458. And let me just double check that I didn't reverse my 9 and 8 in that, like I frequently do by accident. 299,792,458. Yeah, I did it right. Cool. Okay, by the way, that's also 186,000. I'm going to say approximately 186,000 miles per second, or it's approximately 671 million miles per hour. So just to give you a ballpark figure, that's really what the speed of light is, 299,792,458. How fast is that? Well, that's fast enough. If this were the Earth, okay, if this were the Earth, then it would circle around 8 times. Eight trips around equator. In 1.0 seconds. And actually it's right at a little bit less than 1 second, if I'm not mistaken. But that's how fast light is. It's really fast. Still, it takes light a little bit over a second to get to us from the moon. So for instance, the sunlight shines out onto our moon and then reflects off the surface of the moon and comes to our eyes on Earth. We're actually looking at it as it looked about 1.1-ish, 1.2-ish seconds in the past. And in fact, the distance to the sun is 93 billion miles away. If anybody as exciting as me, did the great thing, the fun thing, the awesome thing, like going to a concert or whatever over the weekend. Like you sat in at your house at 7 p.m. and you quickly tuned in the TV to Wheel of Fortune. You might have seen the Wheel of Fortune host suggest that the sun were 186,000 miles away. And then in the next commercial break, you see him correct it to say it's 93 billion miles away. And then the next commercial, or maybe 2 commercial breaks later, he said that actually the 186,000 was the number of miles light travels in a second. So he actually did all that stuff. But yeah, we are seeing the sun, since that's 93 billion miles away, we see it as it looked 8 minutes ago. Okay, in other words, light takes 8 minutes to get to us from the sun. It's 8 light minutes away is another way of talking about it. Actually, Pluto, if you're looking at it several hours in the past because it's so far away. So that's just give you some perspective on that. But that's one of the results that we found as a result of special relativity. So special relativity 1 was the laws of physics are the same for all inertial observers. Okay, so like I said, in this case, what that showed us was simultaneity in one frame need not be simultaneity to everybody. In fact, it's perfectly okay for both of the two conclusions made. For instance, the person in frame one said that the light hit the front and rear parts of the train car at the same time and were therefore simultaneous, whereas observer two said they did not hit at the same time. And both people are right because the laws of physics are the same. Then special relativity. Actually, I should have wrote that a little better than that. It's almost a random function when I decide my handwriting's too bad. Special relativity 2 is that the speed of light is a constant. Independent of motion of the source or the receiver. Any questions on that? All right, so let's look at some other ramifications, and you got to twist your mind a little bit. And this is sort of what Einstein did. Einstein was actually working in a patent office, and a lot of people were coming up with new clock designs and stuff like that. And his family was actually quite mechanically inclined. They basically made refrigerators and repaired sort of refrigerators of the time. So Einstein, unlike some of your typical, or I should say stereotypical physicists that, don't have any manual dexterity and can't build things or stuff like that. That's not the case with Einstein. That's not the case with a lot of scientists, in fact, especially those guys that were in the Manhattan Project. They did all sorts of cool mechanics and engineering and stuff like that. So Einstein, actually having thought about this while working at a Swiss patent office, came up with his general theory or special theory of relativity, and then came up with a way to produce results from it. So let's take a train car again. So here's a train car. Okay, and we're going to equip it with a very specific type of clock, a light clock. And what a light clock does is it fires a little photon of light up from its sort of flashlight system, bounces off the mirror, which is a distance d above, and then it comes back and registers 1 unit of time. Okay. Now, if you're sitting on that train, what you would say is you would say that the light left that little flashlight at the floor at one time, and then returned at that little light in the floor at another time. And that time we're going to call delta t sub O. And that's what's called the proper time. And it's proper time because it was the time between two events that happened in the same place in your frame. So the fact that the beam of light left and returned to the same spot in your coordinate system means that you are measuring proper time. The time between it leaving the left flashlight and returning to the flashlight is proper time, and we give it the symbol delta t0. Now we know that velocity is distance divided by time, so time turns out to be distance divided by velocity, and that means this distance should be 2d over c. Everybody agree with that? So keep that in your notes. Make sure you write that down, even though I didn't take the time to write it down. Proper time means that you measure a time interval between two events happening at the same point in space. Two events happening at the same point in space is proper time, the time between them. Okay. Now,
I'm going to tell you that this train car in reality is actually moving with velocity v to the right. And what we said, observer O1 is riding that train car. There's an observer here, O2, watching the train car go by. Now, the observer O2 sees something different. What O2 sees is the train car moving from here to here to here. So this is what O2 sees. O2 sees the beam of light bounce off of there and then come back here. Now, according to O2, that horizontal distance was the velocity times the time they measured, which you're going to call plane t. Actually, let me kill that. So we know, for instance, that in the first half of time, he saw this object go basically this distance would be d, this distance would be v times delta t over 2. So I think y'all can guess what this distance on the horizontal, on the diagonal would be, can't you? Using the Pythagorean theorem, we're going to get v delta t over 2 squared plus d squared is the distance traveled there. So for us, O2 observers, we'd say delta t is 2 times the square root of v delta t over 2 squared plus d squared divided by c.
Does that make sense to everyone? So just like above, it's the total distance traveled, which in this case would be 2 times the length along the diagonal, because the other diagonal is identical, just the sloping down instead of up. Now, if we take and square both sides, we get delta t squared is equal to 4 over c squared, v squared delta t squared over 4 plus d squared, which gives us delta t squared is equal to, notice when I distribute this 4 over c squared through here, the 4 cancels out and I'm left with v squared over c squared delta t squared plus 4d squared over c squared. Does that make sense to everyone? Any questions on that step?
Okay, well, you might notice that this quantity right here is in fact delta t 0 squared.
You'll see that from the delta t 0 above, the proper timing, remember?
So I'm going to solve for basically delta t squared. So first I'm going to pull the terms with delta t squared to one side, and that's going to be 1 minus v squared over c squared times delta t squared is equal to, in this case, in this case, delta t squared. I forgot I had already made that substitution. So this is going to be delta t0 squared, right? So we can finally say, by taking the square root of both sides and dividing through by dividing through by 1 minus v squared over c squared, we finally get delta t is equal to delta t0 over the square root of 1 minus v over c quantity squared. This is called time dilation. Okay. Do you guys, if y'all have been to an eye doctor, you probably know what it means to dilate your pupils. Does that mean your pupils, the holes in your eyes, got smaller or bigger?
Bigger? Yes.
So what we're saying is time intervals get larger for moving clocks. Because, by the way, there's some simplifications we can make. For instance, we define gamma here as 1 over the square root of 1 minus v squared over c squared. That's defined as gamma. And we also define beta as v over c. So you can see that gamma is actually equal to 1 over the square root of 1 minus beta squared. So you can write this a lot of different ways. That tells us, for instance, that delta t is equal to gamma delta t0. So that's another way of writing time dilation, but it just saves us a little work. Now, if you look at gamma by itself, the lowest v can be is 0, in which case you get gamma equals 1. As as v approaches c, then you get basically gamma approaching infinity. Does everybody see why that's the case? Because you're getting closer and closer to the denominator being 0. So what that tells you is gamma is always 1 or larger. So that's another neat new principle that we've just learned. I'll box it off instead of putting those dots there. Okay, so what that's telling you is, if, let's say we did an experiment where we took 1,000 ice cream cones made by a machine, okay, and we did an experiment and determined how long it would take on average for those ice cream cones to just sit at whatever temperature and melt until it became a cup of water in the cone. In other words, like the white that was the vanilla ice cream is now just like a white liquid that happens to be level with the top of the cup that you had. All the other ice cream having melted and fell out, but you basically just have that. And let's say that turned out to be 10 minutes. If the average was 10 minutes and we had a very small standard deviation and therefore an even smaller standard error, we could say that definitively we expect all these ice cream cones to last exactly 10 minutes, right? Well, if you and your best friend get ice cream cones simultaneously, and your friend is on a spaceship flying by at 86.6% of the speed of light, that's a very specific number for a very specific reason, okay? Then according to your friend, their ice cream cone lasts 10 minutes. And according to you, your ice cream cone lasts 10 minutes. But according to you, watching your friend, their ice cream cone lasted 20 minutes.
because it happens to be, and you can try this for yourself, 0.866 is the square root of 3 over 2. It's 866.025, something like that. But if you put that in for beta, square root of 3 over 2 for beta, you'll end up getting gamma is equal to 2. So your friend being in the car with their ice cream, or in the spaceship with their ice cream cone, saw the ice cream begin to melt and finish melting at the exact place in space, namely in its hand, in your friend's hand. That your friend is measuring the proper time, and therefore the delta T 0 is 10 minutes. But since gamma is 2, that means delta T, what you measure, would actually be 20 minutes. And guess what? If your friend is flying by you in that spaceship and watching your ice cream cone, they're going to say your ice cream cone lasted 20 seconds or 20 minutes, and you're both right. That's what we mean by the laws of physics are the same for all inertial observers. You're both right. Okay. It seems like it's contradictory, and in some sense it is, but it's only in the sense that you can't do both things. You either have to do the experience you had watching the ship go by, or you have to have the experience of being in the ship and watching your ice cream take 10 minutes, watching their ice cream take 20, or us being outside of the ship watching your friend's ice cream take 20 minutes and our ice cream take 10 minutes. So that's what time dilation is about. Any questions on that? Pretty weird, huh? So there exists something called the twin paradox. So I'll go ahead and cover that real quick for you. The twin paradox has been misstated, and that's why I made a point to define what a paradox was for you specifically, because I actually saw it in a book. I don't know if you know this, but Time magazine used to always offer these subscriptions to various things. And if you bought the subscription, then they'd give you this gift, like Sports Illustrated gives you a football phone, or Time Life Books might give you a certain encyclopedia or some other book. Well, they gave this book of science facts. And I was reading it over a friend of mine's house because he happened to own a copy. And it explained the twin paradox and actually got it completely wrong, which was very bothersome, being it's from Time Life Books. But either way, I wish I still had it. I wish I would have borrowed it from him and kept it, or bought it from him or whatever. But either way, the main thing is the twin paradox is this. Let's imagine here's planet Earth. Okay, that's Earth. And me and my twin brother are standing on Earth. Now, the spaceship is going to fly by very, very rapidly. Let's say, I'm trying to think of a speed that I should allow it to travel by. I think I'm going to go with, let's see, 99.995. So this is traveling at 99.995% C. Okay. And it's flying, in fact, to the star Alpha Centauri. Anybody know anything special about that star? Go ahead and speak out loud if you know. It's actually the closest star to us other than our own sun. And it's in fact about 4.2 light years away. Okay. So this spaceship is going to fly all the way there. And then someone on it is going to teleport onto this other spaceship that's moving at 99.995% C this way. and that spaceship is going to arrive here. So this is Mr. Y, me, and this is my brother Brian. Okay, so my brother Brian is going to stay on Earth because he doesn't like things about science and stuff like that. Plus he's a wuss. He'd probably be too scared to do this. So I am going to teleport onto the ship as it's flying by. Okay. And then when I get here, I'm going to teleport back onto this ship. And then when I get back here, I'm going to teleport down back to Earth. Okay. Now, according to Brian, my twin brother, I don't really have a twin, by the way. He's 7 years younger than me, but has way less hair. I just need to say that. Got way less fat too, but I'm going to not pretend like I'm not going to mention that. Okay. He finally got over 200. He's like really happy that he weighs over 200 pounds. Of course, he was like bench pressing like, 385 pounds or something. So he's a beast. But either way, Brian said that he actually saw me leave and then I returned. And what he actually observed is that it took me 4.2 light years. Remember, time is distance divided by velocity over 1 light year per year. That's exactly what the speed of light is, because 0.995 is really close to that. It took about 4.2 years for me to travel to Alpha Centauri, and then it took me another approximately 4.2 years to travel back. So when I got back, Brian saw Billy / Mr. Y. Okay. He saw me, and at 99.995, the gamma factor is 100. So I aged by 4.2 years divided by 100, or excuse me, 8.4 years. So 0.084 years is how much I aged. Now, if you take 0.084 and multiply that times 24, or excuse me, I shouldn't multiply. Let's clear that. 0.084 and multiply that by 12 months per year. That would be me aging approximately 1.008 months. So he saw
question.
Me. Yes.
Oh, sorry.
Go for it.
Just because this, I don't know, I guess I just suck at relativity, but why are we multiplying by 2 when in terms of knowing how much you aged by? Is because I guess you have to travel, or you're, I don't know.
Yeah.
I just
so according to me on my spaceship, I'm going so close to the speed of light that I'm moving at a speed of about 1 light year every year. Well, Alpha Centauri is 4.2 light years away. So in principle, my brother should see me take about 8.4 years, 4.2 to get there. A little bit less because, a little bit more because I'm not actually going the speed of light, but I'm literally going so close that it's only a 1 month difference. Okay. So I had to go 4.2 years of travel to Alpha Centauri, plus a little bit of change. And then I teleported to the other spaceship and flew another 4.2 years, plus a little bit of change, and then teleported back to Earth. So that is how long the trip would take, just because how far Alpha Centauri is from us. That's why I did two. I got to make it for the trip there and the trip back. Now, when he gets back, these are the facts that he sees. He sees that, in fact, I have now aged not by 8.4 years, but by 1/100th of 8.4 years. And the reason why I said 1/100th is it turns out that gamma is equal to 100 when you have the square root of 1 minus 0.99995 squared.
But wouldn't you also, oh, sorry.
Go ahead.
Wouldn't you also have to factor in the amount of time it takes the light from Alpha Centauri to reach Brian?
We would, but only if we're talking about him seeing Alpha Centauri. So what we're doing is maybe we're using a subspace wormhole that communicates back to my brother and says, and does so instantaneously, which is physically impossible, obviously. But that's the only reason why you do it's 4.2 years. What reality could be is that Brian just happened to know that I was going to be back in roughly 8.4 years. He'd be waiting there and he'd see me and he's like, oh crap. You hardly look older at all. And I'm looking at him and he's in fact now 8 years older. And in fact, that'd be like 8 years and 4 months older. And, you know, he'd have a lot more gray, probably have even less hair than he does now. I'm hoping he'd be fat like me. That would make me feel a little better. Stuff like that. Now, that is not the paradox, but that's what that Time Life book said. The paradox is not that I come back and I've only aged 1 month and my brother's aged 8.4 years. The paradox comes in where Brian tries to argue, no, that's not what happened at all. In fact, what happened was I rode planet Earth and we took off to the left on planet Earth until Alpha Centauri got lined up with my brother's spacecraft. Then he, like an idiot, me, in other words, Mr. Younger, teleported to another spacecraft that was also sitting still. And then the Earth turned around and went back and moved back to where it was, at which time my brother, me, Mr. Younger, teleported off of that second spaceship and landed on Earth. So my brother would claim, no, I should only be a month old, and he should only be a month older, and his brother should be 8.4 years old. That's the paradox, or that's the supposed paradox. The nature of science is that if you have a paradox, you don't understand the science very well. So all of these paradoxes have to be debunked, or else Einstein's relativity is wrong. But it is debunked, and the reason why is this. And I refer to these quite often in my class, but a simple pair of fuzzy dice would suffice. So for instance, if I had fuzzy dice earrings, let's say, because clearly I wear a lot of earrings. I actually do have piercings. I was a punker in high school, so I still got those holes and all that good stuff. But anyways, if I was wearing fuzzy dice earrings, when I teleported from the Earth to that first spacecraft, you can be sure that these earrings would swing wildly towards the back of the craft as I landed on it, right? Because I went from 0 miles per hour to 99.999 or 995% of the speed of light. So my earrings would swing backwards. And then when I teleported from that first ship to the other ship, I literally went from going 99.995% of the speed of light this way to 99.995% of the speed of light this way. So my fuzzy dice would swing that way. And then when I got back to the Earth, I would teleport down to Earth, and of course my earrings would flail to the left again, where I went from 99.995% of the speed of light to 0. Okay, so there's an experiment I can do that tells which one of us actually moved, and the experiment is that the fuzzy dice earrings moving shows that I was in fact the one that moved, not my brother.
My brother could wear his fuzzy dice earrings, which he does regularly, I'm sure. My little brother could wear his fuzzy dice earrings, and they would not be bothered at all. And hence, we can show that I am the one that traveled and not him. So, in fact, if this experiment were done, I would come back being only 1.008 months older than when I left. And that's because my time was dilated. Right? My clock, my heart, which beats, roughly 1 beat a second, which, if I'm asleep, it does. If I'm actually walking or talking or anything, it's more like, 1.3 beats per second. But that's going to slow down. And what made it slow down is the laws of relativity. And that would tell me that delta, which is why I divided by gamma in that expression, because I'm solving for delta t 0, not for delta t, right? The formula was delta t is equal to gamma times delta t 0. So if I want to know delta t 0, I divide gamma, or delta t, excuse me, by gamma, and delta t is what my brother measured, because he saw me leave at the Earth, and then he stopped the interval at Alpha Centauri and then stopped again at the end of my trip back. So he's not measuring proper time. I'm measuring proper time, because my proper time was measured me being in my position each of the 3 times. Okay, so there's no paradox at all. In fact, that just happens to be a fact. My brother cannot argue otherwise. Any questions on that? Okay. Any questions on that? So that's one of the big things that comes out of physics. There's something called the twin paradox, and we've just debunked it, that twin paradox is not a paradox at all. It can be completely understood. And in fact, the other person claiming, since all motion is relative, why didn't he and the Earth just claim that they went to the left instead of to the right like the spaceship did? And he said the spaceship stayed in the same place. The Earth went to the left until Alpha Centauri lined up with my brother, where my brother was. And then the Earth came back going to the right until it lined back up with where my brother was when he left. And therefore, he would argue that he's only a month older and I'm 8 years older. He can't make that argument because we can tell exactly which motion occurred. That's one way of saying it. Okay. In other words, it's not that quote unquote relativistic. So that's something about time dilation that's kind of interesting. So now let's show you another problem. Let's say, whoa, I got my eraser out for some reason. A muon, that's the symbol for it. A muon travels at 86.6% of C from our upper atmosphere. It turns out muons are actually created in our upper atmosphere from the intermingling of the radiation and what they call the solar wind, which is actually particle radiation coming from our sun, interacts with other particles in the upper atmosphere, and collisions occur such that muons are produced. And then lo and behold, we actually can detect the muons down on the surface of the Earth. So the muon is going to travel at 86.6% the speed of light from our upper atmosphere to the Earth's surface.
However, muons have a lifespan of about 2.20 times 10 to the negative 6 seconds, or 2.20 microseconds. Okay. So A how long will us on Earth see the muon live? And B, how far could it travel in that time? Okay. So we know that delta T is equal to gamma delta T0. Now what we got to figure out is that 2.20 microseconds, is that the proper time of the muon, or is that the other time? Remember, the proper time is the time measured by something seeing the events that you're timing between happening in the same point in its coordinate system. So if you imagine, to make it a sentient being as opposed to just an inanimate particle, we can imagine that perhaps a who, as in Horton hears a who, we can imagine a who is riding the muon. Does that make sense? So we got a who riding the muon. It would say, I was sitting here and all of a sudden, boom, this muon appeared and I was riding it, right? And then boom, all of a sudden the muon disappeared right from under my butt again. So the who would say that the muon was created under its butt and then in fact disappeared under its butt and was therefore in the same point in its coordinate system both times. In order for that to happen, the who must be moving along with the muon, therefore the muon's life is the proper time. Does that make sense to everyone? So delta T is equal to gamma times delta T0, and gamma is equal to, for starters, I'll write this as 2.20 times 10 to the negative 6 seconds. And gamma is 1 over the square root of 1 minus 0.866 squared. Okay. In other words, by changing that decimal or that fraction into a decimal, then I actually got beta. So that's why I introduced beta, is we can just write stuff like that. We don't have to write anything else, because beta is literally V over C. Now, I happen to know that when beta is 0.866, gamma turns out to be 2.00. So this is 4.40 times 10 to the negative 6 seconds. So delta T for us is 4.40 microseconds. So even though the particle only lasts 2.2 microseconds, we see it living a good life of a whole 4.4 microseconds. Does that make sense? Now, what I'm using here, let me quickly do something. I'm going to share screen again. Let's see. This time I'm going to share a different screen. I'm going to share this screen right here. So this is a neat thing that I like to use, is I just sit up here and I write gamma, and I solve gamma for beta and beta for gamma. So I make a table. And if I want gamma to be 2, then I happen to know that beta solved for gamma is the square root of gamma squared minus 1 over gamma.
So that's what I put in here for this formula. The square root of gamma squared, notice A3 is that 2 there, gamma squared minus 1, close parentheses, divided by gamma. That's what A3 is. So in doing that, I am actually calculating what beta is. So 86.6, which by the way is the square root of 3 over 2. That's, you know, a number you probably already know, hopefully. So when beta is the square root of 3 over 2, we know the gamma factor is going to be exactly 2. When gamma is 94.28%, then it's 3. 96.82 is 4. 97.97, or actually 0.98 is 5. You can see it gets to 10 at 99.498%. It gets to 20 at 99.87. It gets to 100 at 99.99.5. It gets to 1,000 at 99.99.99.5, and so on and so forth. So that's why I just grabbed these numbers. Like earlier, I used gamma factor of 100, and I knew that was 99.995% of the speed of light. So that's what I was using there. Just makes it a little bit easier to quickly come across and with a valuable quantity. So let me show you what I was actually using. We know that gamma is defined to be square root of 1 minus beta squared, and then you solve that for beta, and you get that beta is equal to the square root of gamma squared minus 1 over gamma. And I know I'm talking to you as if that you were looking at a screen. That's because I had a brief mental fart. So is it back now? No. Is it back? I can't see it. Oh no. No. What screen are y'all looking at, I wonder?
Your home screen.
It was okay. So what I would do now is open this and open this. Hey, where'd my computer go? It literally just disappeared. Okay, so that's this expression over here. This one and this one are the two that I just used. Okay, now for part B, I'm asked how far could it travel? Well, from our standpoint, it's traveling at 0.866 times the speed of light, which is 792,458 meters per second. So if I multiply that out, I get clear 299,792. I'm being pedantic here. 458 times 0.866. That gives me 2.60, which I might call 2.602 times 10 to the 8th meters per second. What you're normally going to use for the speed of light, by the way, is C equals 3.00 times 10 to the 8th meters per second. So that's good enough. But anyways, I just use that. So that's the speed that we, as Earthlings, see the muon going when it's traveling at 86.6% of the speed of light. So now I can say distance is equal to velocity times time, and say the distance we think it can travel is equal to 4.4 times 10 to the negative 6 seconds, and that's 40, by the way, times 2.602 times 10 to the 8th meters per second, carrying that extra digit of the 2. So I'm going to multiply this by 4.4 e to the negative 6. And I get 1,142 meters. That's as far as it can travel. Okay.
Now, we can explain this now from a who standpoint. We can realize that from a who riding a muon, actually we can understand it from our standpoint, but not from the muon standpoint. From the muon or the who that's riding on its standpoint, the muon's not moving, right? So its time is not different. In fact, the muon, the who riding the muon is measuring out time, and he knows that the muon is going to cease to exist at 2.2 times 10 to the negative 6 seconds. And that's a fact. There's nothing you can do about it. However, the laws of physics are the same for all inertial observers, according to the special theory of relativity. So with that in mind, both the who and the us have to agree that the muon went as far as it did travel, right? If in fact, if that muon was created in the upper atmosphere and hit the surface of the Earth, both the who riding the muon and us watching the muon come to Earth, both of us as different observers would observe that the muon hit the surface of the Earth. So how do we possibly explain that from the muon's point of view? The muon does not see the who does not see the muon moving at all, so it can't be time dilation. And the speed of light's a constant, which means the distance over time has to always equal a 299.792.458. So what must happen in addition to time dilation? What other variable can you alter other than time?
Space.
Yes, space. And in fact, that leads us to reach the conclusion that there must be something that happens to space as well, because in the who and the muon's frame, time is not affected at all. Yet both us and the who would agree if the muon actually made it to the surface of the Earth, that it made it to the surface of the Earth. So that introduces us to something other than time dilation, and that's called length contraction. Okay. So with length contraction, we can actually figure out what that is. We can, again, use our same idea about velocity is equal to distance divided by time. And we could say, if we saw a spaceship flying by us, okay, if we saw a spaceship flying by us, it would take the length of that spaceship divided by its velocity for the whole spaceship to pass us. So we would say delta T has got to equal the length of that spaceship divided by the velocity. So like if it's a cruise ship, but a cruise ship that say was a whole light year long, and it traveled by, say, half the speed of light, then we'd say, okay, well, that cruise ship was a light year long and it's traveling at half the speed of light, so it should take 2 years to go by us, because 1 light year divided by half a light year per year, which is what half the speed of light is, gives us 2. Does that make sense? Now, according to the spaceship is seeing something different. The spaceship says its time period, which is delta T 0, because if you're on the spaceship or you're on the ship that's riding by, you're measuring the length, say, at 2 different locations. And what you find is that the delta T 0 that you measure should be equal to delta T times the square root of 1 minus V over C squared. Okay. Which is in fact delta T over gamma. So you can now use that for delta T. Delta T is equal to delta T, delta T is equal to gamma times delta T 0. And from that, you get L is equal to L0 over gamma, where L0 is called the proper length. again, the word proper here sort of sounds wrong in the English language. It doesn't mean it's the right one. It just means the one that's measured in a very specific way. The length of an object moving relative to an observer is measured to be shorter along its direction of motion than when it is at rest. So I like to tell students that if you take, for instance, the old police cars that they had in the 70s and 80s, which were Crown Victorias, they're these big Cadillac looking cars. They're really long, right? If you travel in a Cadillac or in a Crown Vic at 86.6% of the speed of light, it's going to go from like an 18-foot long car to like a 9-foot long car. But the dimension perpendicular to the velocity, in other words, the height from the bottom of the tires to the top of the cab, is not going to change at all. So it actually transforms it to look something like a Volkswagen Beetle or something. So just like time slows down for clocks that we say are moving with respect to us, in this case, we say that objects shrink from their normal length when they're moving with respect to us. And the formula that we use for that is this: the proper length divided by gamma. Remember, gamma is always 1 or larger. So the proper length divided by gamma is, in fact, the length that we observe. So now we can go back to our muon and our who. So we'll say, how far does the who writing the muon think the 1,142 meter trip is? Okay. So in other words, we determined that actual muon or who saw the particle, was riding the particle and came towards us. We saw that it moved a distance of 1,142 meters. That's from our frame. So what we want to know is what distance does the who think that is. So we want to know L0, and we know that L is equal to L0 over gamma. So this tells us that L0 must be equal to gamma times L. Well, L0 therefore is 2, because that's what gamma turns out to be, times 1,142 meters, which is 2,284 meters. So you actually, in introducing it this way, by thinking in terms of c being a distance divided by a time, and that always being a constant, tells you that both space and time have to be manipulatable in some sense. In other words, space and time are relative. What one person measures as a distance, another person is not going to measure the same. Okay, so you can do neat little problems like if you have a, let's see this one. I'm going to choose another nice value of gamma. Okay, so let's say example 3. We have a 24-inch by 18-inch photograph like this. The photograph or painting or whatever. Whoa, where to get out of that from? Is traveling to the right at, let's see, 0.9950. see what do we see as its dimensions. So maybe we say there's an X here, and let's say there's a circle here and a circle here. That's what our painting, our picture is going to be of. Okay. Maybe it's cross members in a bridge or something like that. Okay. So L01 is 24 inches and L02 is 18 inches. Okay. And we know that's the proper length because that is the length that you would think your vehicle is, or in this case, if you were a who writing this painting or photograph, that is the length you would measure by extending a tape from you standing on one edge, extending a tape measure out to the other edge. Okay, so that's the actual proper length. But we're going to see that thing moving by with a velocity of 0.9950 c. Okay, so that's what the velocity is that. So what we determine is we want to know L, which equals L0 over gamma. So I'm going to say L1 is going to be L0, which I say is 24 inches because I'm talking about the dimension that's going parallel to the velocity, which is the 24 inches. And I'm going to divide that by gamma, which gamma is in fact equal to 10 for that particular beta. Okay. So what I'm saying is 1 over the square root of 1 minus 0.9950 squared is equal to 10. Okay. So that means this is going to be 2.4 inches. So that painting to us will look like this. Actually, the height shouldn't change at all, in fact. So I'm going to do like that. And I'm going to say it's like this and this. Now the picture has become something like that, where this dimension is still 18 inches, but this dimension is now 2.4 inches. Any questions on that? And you can, for instance, imagine what the windshield angle of a car would be. So you can actually look up, say, a Lamborghini Diablo or a Ferrari Enzo or a 1967 Volkswagen Beetle or a 1967 Volkswagen Super Beetle, anything you want, you can look it up and they'll actually have listed what the angle of incline of the windshield is. And you'll know that basically for a windshield, you'll have some angle theta like this that can be represented by a right triangle. And if the car is actually, whoa, how did that switch to that again? There it goes. So if that whole thing went crap. So if the car initially had this angle, what you're going to see happens when it actually travels at some velocity v, then it's going to go like this. This dimension right here is going to shrink, and that dimension upward is going to stay exactly the same. And the angle will now be this new angle. Let's say, I shouldn't use gamma, I guess. Let's undo that one. Let's say the angle alpha now. Okay, so that's what happens with geometry and geometric shapes. just like that X that was probably at a 30-degree angle on the photograph that I did in example 3, that went to like a really steep X. So that's some of the stuff you can do with length contraction and stuff like that. Again, I highly recommend you work with gamma, solve it for beta, work with beta, solve it for gamma, and then make like a spreadsheet that you can just go to from time to time to see, you know, what kind of speeds cause what kind of gamma factor. Because the gamma factor is how much the time is going to increase by. In other words, what do you have to multiply by proper time to get the time that we would see? And then gamma is also the number that you'll have to divide the proper length by to see what length we would find it. In other words, by what factor does it get smaller? So all that stuff is kind of neat to play with, but it's nicer if you actually know the values. What I like to do is I assume that V over C is like a fraction. Let's say V over C, for instance, right? And then I solve for bits in which V and C are whole numbers, or the square root of a whole number or something like that. And then you can do all these different values so that you get like root 3 over 2 is obviously going to be gamma equal 2 and stuff like that. Any questions on that? Okay. So now, in addition to all that, those two things that happen, Einstein is actually able to show quite a bit of other stuff as well. For instance, if you wanted to, why did I get over the way to here? If, for instance, if you wanted to figure out what way we can still use Newton's laws of motion, you need to know what is the mass and what is the momentum. Because remember, Newton's second law was the net force is equal to dp dt, and we define the mass, the P, the momentum, to be m times v. Well, if you wanted something to behave like m times v so that the force was equal to it, it turns out there's only one real way you can define momentum. And momentum turns out to be no longer P equals mv, which was a classical momentum. It turns out, in fact, that P has to be gamma times m times v. If you do that, then lo and behold, we're lucky enough that all the laws of physics stay the same. In fact, this would be consistent with, whoa, read it when it does that. This would be consistent with relativity. So that the summation forces is equal to dp dt. Only works technically if it's gamma times m times v. Okay. And in fact, I'm not going to require you to do any of this kind of stuff with it, but it turns out that if you want to treat momentum as a vector, it's more convenient to treat momentum P as a 4 vector. And the time component of it would be the energy of the particle or the object divided by the speed of light. Then it'd be gamma m v sub x, gamma m v sub y, and gamma m v sub z. So that's another way you could do it, and that's called a 4 vector. I'm not going to require you to do that. I think your book mentions it in like some of the footnotes or something like that. But that's one of the things we have to give up on. We have to say momentum is no longer P equals mv. Momentum is now gamma times mv. And if you look at doing a binomial expansion, for instance, for gamma, you'd see that really the first term is essentially 1. So until you get v comparable to c, you can continue to use mv, and that works just fine. So let's try a problem. Let's compare the momentum of an electron when it has a speed of, so this will be example 4. E minus has a speed of 3.0 times 10 to the 7th meters per second. Okay. And then let's see what the momentum is. And then part B, if the V of the electron is equal to 0.995 C, what is P? Okay, so I'm just using the symbol P to remember our momentum. So what, for part A, we're using P equals gamma times M times V. Well, gamma would be 1 over the square root of 1 minus 3.0 times 10 to the 7th meters per second divided by 3.00 times 10 to the 8th meters per second. Times the mass of the electron, which is 9.109 times 10 to the negative 31st kilograms times 3.0 times 10 to the 7th meters per second. So if I do the math, you can get 1 over the square root of 1 minus 3.0 e to the 7th divided by 3 e to the 8th is equal to 0.1. So that's 0.1 right there, times 9.109 e to the negative 31 times 3.7 e to the 7. So this part would be times 3.37 times 10 to the negative 23rd kilograms meters per second. That's basically the classical momentum would be this. So this is P classical. But you can see this part right here is 1 over the square root of 0.9. So 1 divided by the square root of 0.9. Excuse me, not 0.9. I forgot to square it. I should write that here so everybody remembers that that's got to be squared. So what I'm going to do is 3.0 e to the 7th divided by 3 e to the 8th. And now I'm going to square that. So that's 0.01. So I just made the correction on here. I changed it from 0.1 to 0.01. That's obviously 0.99. So 1 divided by the square root of 1 minus 0.01 is 1.00504. So if I multiply that 1.5004 times the 3.37 times 10 to the negative 23rd, I get 3.39 times 10 to the negative 23rd kilograms meters per second. So you can see 3.37 versus 3.39. I went down literally by 1%. So at 1% of the speed of light, the momentum only changed by 2 places in a non-significant figure. In other words, it would in fact still, both cases would round to 3.3
or excuse me, 3.4. So there wouldn't be any difference really if I was following my sig fig rules.
Now for part B, things going to get a little bit more hairy. We're going to say P is equal to 1 over the square root of 1 minus, in this case, it's 0.995, or did it? Yeah, I did 995 squared times 9.109 times 10 to the negative 31st kilograms times 0.995 times 299,792,458 meters per second. This would be the classical momentum. So 9.109 e to the negative 31 times 0.995 times, that gives me 2.72 times 10 to the negative 22 kilograms meters per second. But this factor right here is going to be quite a bit different. I'm going to say 1 divided by square root 1 minus 0.995 squared. That's going to give me 10.0125. So I get, in this case, the final answer is 2.72 times 10 to the negative 21 kilograms meters per second. That's what the actual momentum is. And notice that's a stark difference between 2.72 times 10 to the negative 22. It's literally a whole factor of 10 larger. So once you start getting to, there's a couple ways of looking at it, but once you start getting above 1% of the speed of light, it's going to start to come into the digits that are significant. So around 1% of the speed of light, you can sort of ignore it. There is a difference. It usually will be in the second decimal place, something like that. But as you get a larger and larger fraction of the speed of light, the more significant the change will be. And in fact, in this one, you can see that it's 2.72 times 10 to the negative 21 versus 2.72 times 10 to the negative 22. It's a whole factor of 10 larger. Any questions on that?
Yeah, I was wondering if you could give like a basis, just like general understanding of the first one, the first equation that we solved for using 3.0 times 10 to the 7.
Okay.
Why didn't we just put 3 times 10 to the 7th in parentheses and have to divide by the speed of light?
Okay, you could have done it that way, but what I gave you was the actual speed in meters per second. So what you had to do was take gamma and then multiply it by m and then multiply it by v. So in part A, I had to compute gamma, which included the 3.0 times 10 to the 7th. Notice that's down there in the
because it's v squared over c squared. Okay, exactly. Yeah, I forgot that.
Yeah, and don't forget there is a 2 there that I had to write after the fact.
Right, the squared.
Yeah.
Yeah, got it.
Okay. But in that case, like I said, it was only 1%. Or in this case, it was what, 10%? Yeah, it was 10%. Yeah, 10%. And it only mattered in the second decimal place. So it wasn't that big. But another rule of thumb is whenever the kinetic energy of the particle is comparable to the rest energy, which y'all have all heard of E equals mc squared, that's the rest energy of a particle. So if you multiply the mass of the particle times c squared, that'll come out in joules. If you compare that to the kinetic energy in joules and they're about the same size, then you need to be using relativity, not classical physics. Okay. So that's what momentum is. It turns out other things occur as well. And in fact, Einstein actually mailed this in the day after he mailed in his paper on relativity, the dynamics of or electrodynamics of moving bodies. He said, sent in an appendix the next day. It's all handwritten, sent to a German a German journal. He said, by the way, I discovered this E equals MC squared. Well, that's another thing he could have won the Nobel Prize for, because with E equals MC squared, not only were we then able to figure out that we could make a really, really horrible bomb, but we were also able to figure out why the sun could actually live as long as it did, because I kid you not, at this point in time, the only thing we have to understand the length of the sun is, or the length of the lifetime of the sun, is by assuming the sun's made of a giant lump of coal. And Lord Kelvin had calculated that that could last up to 50,000 years roughly. Well, that was fine, you know, when we took our oldest chronicle of history, which is essentially the Old Testament. Obviously, the Epic of Gilgamesh is a little bit older, but it doesn't really chronicle history in any kind of way. So if we take our Old Testament and we see that, you know, adding up the begats, you know, Adam begat such and such at such and such an age, and then he begat such and such at such and such an age. You add up all those begats until you get to a character we know in our history books, which is Nebuchadnezzar. You can figure out that basically we think the earth should be around the order of 10,000 years old. So that was perfectly fine with Lord Kelvin's calculation. But we had started discovering from biology, from geology, and stuff like that, we had started discovering the idea that the earth might be hundreds of thousands or maybe even millions of years old. If that's the case, then how could it possibly exist with a sun that's only going to live for 50,000 years? Well, E equals MC squared was the answer to that. Because it turns out that what goes on in the core of the sun, and stars that are like 0.5 times the mass of the sun or smaller, they can actually circulate material in and out of the core of the sun, so that the sun can really, the star can really burn all of the mass as a fuel. But our models, which are solar models, which are sort of like global circulation models that we use for modeling climate change and stuff like that, our models tell us that the stars, once they get about a little bit bigger than 0.5, the mass of the sun, they no longer have a circulation mechanism that allows particles of hydrogen to come into the core area, where it's the only place that's hot enough for nuclear fusion to go on. So whatever we have in that inner 10% or 20% of the radius of the star, whatever atoms are in there, they're the only ones we get to burn. So what we're doing is we're taking 4 hydrogens, nuclei. It's so hot, it's a plasma. It's about 16 million Kelvin inside the center of our sun. We need at least 10 million Kelvin for 2 protons to run into each other. Then their average kinetic energy will be high enough that they can actually overcome the Coulomb barrier and hit each other, even though they're both positive. And when that happens, one will spontaneously turn into a neutron. And then another one will come and stick to it. And then you got 2 protons and 1 neutron. Another one just like that, 2 protons and 1 neutron, will then combine with it and make 2 protons and 2 neutrons, which is the helium nucleus. If you add up all the masses of the 4 protons and the masses of the 2 protons and 2 neutrons, you'll find that mass is actually different than the mass of the helium nucleus. And that difference in mass multiplied by c squared is the amount of energy that's given out each time that reaction occurs. Some of the energy is in photons, some of the energy is in antimatter, specifically positrons, and there's also neutrinos that come out as well. But then all you have to do is take the total amount of energy the sun's putting out and divide it by that energy per collision, and that can tell you how many collisions are occurring every second. And that can tell you how long how big the gas tank is, basically. So how long the sun will live. And by that calculation, we get that the sun can live about 10 to 11 billion years old as a hydrogen burning star. Okay. So that's another big thing. E equals MC squared. And not only that, E equals MC squared, we often write it as delta E is equal to delta M times C squared. But that happens to be true in everything. It's not just E equals MC squared in nuclear physics. For instance, if you took, now this is a big point here. If you took, for instance, a brand new car right off the assembly line and you cleaned it up, everywhere that fuel and exhaust will go through will be perfectly vacuumed.
We will look at it with a subatomic microscope so that we can even remove individual atoms or molecules along that path, get it perfectly clean, put it all back together perfectly clean in a perfectly clean room, and then fill it up, say, with 10 gallons of gas. Okay. And we will weigh that 10 gallons of gas to, let's say, 18 decimal places. Okay. Now we take that 18 decimal place mass of gas, okay, and we run the car for a period of time until the gas runs out. And then we do that whole cleaning process again, only this time we actually weigh every bit of stuff that was left in the train, basically from the carburetor or fuel injector, whatever it has, all the way through the pistons, any matter that's built up in there that's obviously expelled or let off fuel parts and stuff like that. We add all those little atoms and molecules masses up, plus we add all the masses of all the exhaust that was put out. And if we did that, what we would find, again, assuming we can measure it to like 18 decimal places, what we would find is that mass of all that stuff in the exhaust and in the particles from within the engine and the exhaust manifold and all that good stuff. If we weighed all that, that weight would still be less than the weight of the 10 gallons of gas. If you could measure it again to like 18 decimal places. Now, if you take that mass difference between the 10 gallons of gas and all those particles and all the exhaust particles, and you multiplied that by c squared, you'd find that's exactly the amount of energy that was created by the car engine burning that fuel. So that's what I mean when I say E equals mc squared is true all the time. If you have any energy, that energy had to come from the loss of some mass. So when you bind 4 hydrogens to 1 carbon, for instance, the mass of the carbon atom and the 4 hydrogen atoms, add all of them up, what you will find is a mass that's small, that's actually bigger than the mass of the CH4. So in other words, if you look up the mass of CH4, you're going to find one number. If you look up the mass of carbon and then the mass of hydrogen and multiply the mass of hydrogen times 4 and add that to the mass of carbon, there will be a small difference in mass. And that small difference in mass multiplied by c squared will be equal to the binding energy of the carbon. So E equals mc squared is there for everything. Not only that, we can't, I already showed you that we can't use P equals mv. We had to use P equals gamma mv. We also can't use kinetic energy classical was 1/2 mv squared, which we could also write as P squared over 2m. That was classical. But in relativity, kinetic energy is gamma minus 1 times mc squared. So that's another change. In fact, there's another equation for energy that gives us E squared is equal to P squared C squared plus M squared C to the 4th. That's another important thing. And for instance, if you're talking about photons, which are the massless particles that make up light, since they're massless, this term is 0 for a photon. So the energy is just P times C for a photon. So that's something that's kind of neat. So we've seen everything sort of changing. The energies has to change. We can still use it the same way we used to, but the problem is we have to use different definitions for things like kinetic energy and momentum and stuff like that. Now, in addition to that, velocities don't add the same way. That's another weird thing. And I can show you a neat way, but what we really need to look at in order to get it is something called the Lorentz Transformation. And it's called Lorentz Transformation because Lorentz was the one that first did it. And here's what happened. So when we first discovered that light was in fact a wave, where we had been doing that for some time. Huygens, for instance, had been working out as light was a wave and got a lot of laws of physics for optics and stuff like that were consistent with it being a wave. But Newton had done more or less everything that Huygens had done by treating light as particles. So in the 1810s, 1820s, 1830s, there was still an ongoing debate. What is light? Is it particle or is it wave? And ultimately what we figured out is it has to be both. It's called the principle of complementarity. And that's what you'll learn about in quantum mechanics. But anyways, it has to be able to be both. And then Louis de Broglie will take that argument and say he couldn't imagine God making it such a non-symmetric universe where matter doesn't also behave like a wave. So he just postulated that matter is going to look like waves too. And he was right, by the way, and won a Nobel Prize for it. But anyways, that's why all that came out. Well, in the 1860s, Maxwell's equations were released and people were starting to understand them. And you could get a wave equation that I've told you about before. And when he derived that, he was in fact the first person to know definitively exactly what light was. Light was a wave. Specifically, it was an electric field oscillating, let's say vertically. That would be called vertically polarized light. If the electric field was oscillating left and right, it would be horizontally polarized light. But let's take the vertical case. And then perpendicular to that electric field is a magnetic field that's going this way, left and right. And then a third direction straight ahead, all three of them mutually perpendicular. That's the direction the light is traveling. That's what Maxwell's equation told us light was. Okay. Well, we had never seen waves except for waves in material. We'd seen ocean waves, which obviously travel in the ocean. We'd seen sound waves that travel underwater, but way faster. For instance, those of you who scuba dive, you know that sound is omnipresent, meaning it comes from every direction because the speed of it's so much higher. Not because the density tends to slow it down, the higher density, but the rigidity of it tends to speed it up, and that more than compensates. So it's a way faster underwater. And sound, in fact, is a wave in air as well. So we had no idea that waves could exist except in material. And we knew after Maxwell that the radiation coming from our sun had to be waves. And the only way that could be is there had to be some material out there, and they called it the ether. And the ether was presumed to exist. And then finally, Michelson and Morley run an experiment where they're going to send out two beams of light at perpendicular angles. And the beam of light will bounce off a mirror and then return back. Well, if one of those beams of light happens to be going parallel to the motion of the Earth through the ether, then the time taken for it to go from the source to the mirror back to the source will be the distance between the mirror and the source over C minus V plus the distance between the source and the mirror over C plus V, because one way it's going to go with the ether, and the other way it's going to go against the ether. Well, that turns out to be a distance of basically 2L over V squared minus C squared, something like that. Now, the other one going perpendicular, that's going to be different by a square root of V squared minus C squared. And when they did the experiment, they suspected that it would be off by a certain amount. So you'd get a trough lining up with a crest so that there would be some cancellation. You get these fringe effects. And when they did the experiment and turned it 90 degrees too, they found that they basically got a null result. In other words, they could not detect the motion of the Earth within the ether. So Lorentz tried to figure out some way to make sense of that null experiment without getting rid of the ether. He realized that it was off by a factor of a square root of 1 minus V squared over C squared, or you can also treat it as a square root of V squared minus C squared. And he basically argued that maybe the ether mechanically transforms such that its length along the motion compresses by a factor of gamma, basically gamma from relativity. Only this was before relativity. So he worked out these equations that are called the Lorentz transformations, and everybody was like, well, that fixes it, but that's a moronic, law of nature for it to behave that way. So along comes Einstein and actually gets the exact same equations, but by a much better method, and that's by those two principles of special relativity,
that I told you existed. The laws of physics are the same for all inertial observers, and the speed of light is a constant independent of the motion of the source of the observer. So what the Lorentz transformation equations are, oh man, I hate it when it does that. 0 for a photon. Okay, so let's imagine a coordinate system right here. Say this is X and this is T. And let's imagine a few seconds later, there's another coordinate system, X prime, T prime, and it has a specific position X1, T1 right here, okay? So we could say that in fact, X would be equal to V times T if this frame, by the way, is moving. Let's actually make it a U. I'm going to make it a U instead of a V. Let's say this velocity is in fact U. That's the velocity that the frame is moving with respect to the other frame. But we're going to go on the assumption that X equals X prime equals 0 at T equals T prime equals 0. So when you first started watching, the two origins and the two axes lined up perfectly. They were right on top of each other. But the prime coordinate system was moving with a velocity U. So X thinks the point X1 is found, or the non-prime coordinate system thinks that X1 is found at UT plus X1 prime. Okay. Now the Y1 is equal to Y1 prime, and the Z1 is equal to Z1 prime, because those it's not moving in those coordinate directions at all. And in fact, from Galilean relativity, you would say that T1 is equal to T1 prime. Okay, that's all Galilean. Relativity, which we covered in, I think, chapter 2. But if you want to find out what Lorentz said, all you have to do is you take X and say that's equal to gamma times UT plus X prime. And now I have to put a prime on that and that. Y is equal to Y prime. Z is equal to Z prime. But here's the real kicker. T is equal to gamma T prime plus U times X prime over C squared. That's the Lorentz transformations. So if you want to find coordinates for something in a particular frame, you use these coordinates. These transformations of coordinates. Now, if you want to know what the equations for X prime, Y prime, Z prime, and T prime are, all you have to do is replace all the X's and T's with primes and all the X primes and T primes with non-primes, and change the addition to subtraction. So writing this over here, just trying to make some space so I don't have to put it on another page, I would say X prime is equal to gamma UT minus X, and Y prime is equal to Y, and Z prime is equal to Z, and T prime is equal to gamma T minus UX over C squared. Okay. So that's the Lorentz transformation. Notice all I did was switch the primes with the unprimes and change the pluses to minuses. Now here's something neat. Because we know what they are, I can say dx prime is equal to, looking back at this equation, the x prime is gamma ut minus x. So I'm going to say it's gamma times u times dt.
And notice when we're using the x prime, we got the minus. So this is minus dx. And now I can say the dt prime, looking back at this, the dt prime is in fact gamma t minus ux over c squared. So I'm going to say gamma, and there's parentheses around here, gamma times dt prime, or dt, excuse me, minus u over c squared dx, like that.
Why would you be subtracting it? Wouldn't it be adding it?
So I'm using the prime side, so I'm using the blue equations, not the red ones.
Oh, okay. Sorry.
I just took the differential everything. No, that's perfectly understandable. This is a weird thing to do. The first time I did it, I thought it was absurd. You can sort of think of them, these dx's in the derivatives, they're actually called one forms. So if you want to look that up sometime, you can, but they're called one forms, and they're actually mathematical entities by themselves that you can manipulate like I'm doing here. So if I want to know v prime, in other words, the velocity as seen from the prime coordinate system, that would be dx prime over dt prime, right? Well, you can see that's gamma u dt minus dx over gamma dt minus u over c squared dx. So what I'm going to do is divide top and bottom by dt. So I'll say 1 over dt over 1 over dt, like this. And now I'm going to get v prime, which equals dx prime over dt prime. That's going to, in fact, give me u minus dx over dt over, actually, this just becomes 1. Sorry about that. 1 minus u over c squared times dx over dt, which is basically the velocity of the frame, that's what u is, minus v over 1 minus uv over c squared. That's exactly what it was when I first introduced relativistic, or excuse me, Galilean relativity. And then I said, well, actually, it's actually VAC is equal to VAB plus VBC over 1 plus VAB VBC over c squared. You see that looks exactly the same. The only difference is I'm doing the minus part, which you'd have to do if you were considering it from the prime frame as opposed to the regular frame. So I can do this exact same thing again for dx and dt using the red equations instead of the blue ones, and I would get the plus signs. So do this with x and t, and, well, I'll say and you will get this result. Whoa, minute. Any questions on that? Okay, so it turns out there's a lot more complicated story, but if you're just keeping the axes all parallel and you're just moving parallel to the x-axis, this is plenty equation that you need, and we've got it all done now. So this is basically covering everything. The only thing I didn't cover was the Doppler shift. I'm not going to cover it. I'm not going to test you on it. I think I meant to get all the Doppler shift problems out of the homework, and I think I did. If there's one in there, just try to do your best. I might take off points later. if there's one in there, but I think I got rid of all of them. But that concludes our relativity. If you look in this week's module, you'll see, I think 8 links to my YouTube channel. I did a special relativity 001, 002, 003, 4, 5, and 6 back in April, I think, of last year. And then I did a couple different problem solving examples, and I put those links on your module for this week as well. But that's it. So remember, next time we will meet. I will discuss chapter 11 a little bit in case anybody needs any help with that. I will take questions on chapter 36 as well. But your next test will be during lab, which is right before this on Wednesday, 2 days from now. And it's going to cover the chapters. What did we say they were? 8 and 9, I think. I'll go back to double check. It's in this week's module, or actually it's in last week's module. So let me click on that real quick. And let me stop sharing.
I think you said 8 and 9.
It did say 8 and 9. Thank you.
I think, well, I can go back because I think there was confusion about the 5 and 6 being there.
Yeah.
But,
yeah. So the 5 and 6, we had already tested you that on the midterm. So that was a mistake by me. But since it's open now, some of you never took it, and that's going to make you lose at least one whole extra credit point, because that's a 0 out of, several tests that you're going to get. So I would definitely recommend you take it and, get a decent grade on it. You probably know the material already because you've already been tested on it in most cases. But the practice test for chapters 8 and 9, that's what you should be doing to prepare for the face-to-face test in lab, next lab, which would be Wednesday, 2 days from now. Okay. And what I put in this week's module is chapters 11 and 36 are in there. They're all due basically the 17th, but since there's 2 parts to the chapter 36 homework, I gave you till Wednesday of next week to do part 2. But there's a practice test 5 and an actual test 5 is already up. That's going to be an online test where you're allowed to use your books, your notes, Google searches, but you've got a very limited amount of time, like 28 minutes, but you get 3 chances. So any questions on that? Well, you folks are free to go. Does anybody need anything off this sheet? I'm going to upload it to Google Docs within, a few minutes. So it'll be up there. The video will be up. It normally takes about an hour to process, and then it goes up to YouTube. If you've subscribed to my channel and turned on notifications, you'll get an email or a text message or something, depending on how you set it up, letting you know whenever something's posted there. So I would recommend you doing that. You feel free to unsubscribe later. I hope you don't, because I would like to get, as many people doing it as I possibly can on my page. Even if you just turn off your notifications, that'd be fine with me. But anyways, you have a good one, everybody. And thanks for coming. And I will see you Wednesday.
See you Wednesday, Professor.
Nice talking to you. See you then. Also, someone was it Sarah that wanted to see me after class?
Yeah, that was me.
Okay. Is this a private thing? Because I can open up a breakout room and you and I can go in there.
I was mostly just wondering what to do